Hello students, today we will extend our lecture on current electricity. We have already done with the Ohm's law and very interesting formulas. So today we will continue. After that we will do limitations of Ohm's law, resistance and resistivity. So let us begin with these interesting things.
Ohm's law has two forms. So if we write on Ohm's law, then first what we studied is V is equal to IR, where V is the voltage, I is the current, and R represents the resistance. And the second form of Ohm's law is J is equal to sigma E, where J corresponds to the current density, sigma is the conductivity, and E is the electric field. So these two are called as two forms of Ohm's law. You can use this law and similarly you can use this law. These are of equal importance. This we are studying since our previous classes, and this is also has the same derived from the same equation, but this also we should remember as would we remember V is equal to IR. Similarly, what we should remember, J is equal to sigma E. J is the current density, sigma is the conductivity, and E is the electric field. So always remember these two for the Ohm's law. So whenever we are talking about the conductors, they are a very good conducting material of electricity. So they have a high value of conductivity and a very low value of resistivity. So they always follow Ohm's law. Whenever you are talking about matters, they always follow this Ohm's law. Follow this Ohm's law. What do you mean by following this Ohm's law? That means whatever is the voltage developed is always proportional to the current. Whatever is the voltage applied to the two ends of the conductor will always have the same amount of current. So let us say that if we want to plot a graph between the voltage applied and the current. So on the x-axis, if we take the voltage applied, that is in volts. X-axis, if we take the current that we are getting, it may be in milliampere or microampere. And current will be large for the conductors, so its resistivity is low. So what we get, because this is directly proportional, so it has a linear relation V is equal to IR. So whenever you plot a graph between V and I for the conductors and these follow the Ohm's law, then you have the graph like this. So you always get a straight line. What does this straight line represents? This straight line represents that it is following the Ohm's law. So for all the matters, they have this linear relation between I and P. So what do we say? That all the metallic conductors, they follow Ohm's law or they have ohmic behavior. This is true in case and that we call as linear current voltage relationship. What this linear relation is? This linear relation is linear relationship between the current and voltage. So current we are getting and the voltage we are applying. So it is very much true that whenever you are taking any of the conductor, it has an ohmic behavior. It has a linear relation between its voltage supply and the current measured. But in certain cases, this Ohm's law has some violations when the Ohm's law is not followed. So these we call as the limitation on Ohm's law. Whenever Ohm's law is violated, in which cases it is violated, let us go quickly to in all the cases where the Ohm's law is not followed. So the Ohm's law is very much clear, and when it does not follow a linear relationship, then there is a violation. In what cases there is a violation? So let us go to the limitations. First limitation is that V is not proportional to I. Our applied voltage is not proportional to the current observed. That means the current and voltage do not follow a linear relationship. Or second case, when the relation between V and I depends on the sign of V. And the third is for the same value of I, that means for the same value of current, V has more than one value. That means the voltage is having more than one value. Okay, so there are the three cases when there is a violation. First, there is not a proportionality relation between V and I. Second is when V and I depends on the sign of V, if V is positive or negative, that means we have altered the voltage, then I also changes. Okay, so I depends on the sign of V. And third is that we are having the same value of I for more than one value V. That means again there is not linear relationship. V has two or more than two values for the same value of I. So in these three cases, the Ohm's law is violated. These are the three cases. V is not proportional to I, that means there is not a proportionality relation. We will not have a linear graph. Second is that the relation between V and I depends on the sign of V. So let us look quickly at how V and I depends on the sign of V. So in the relation between V and I depends on the sign of V. As you can see that here we have taken, this shows a graph when the V on the x-axis we are having the voltage and y-axis we are having the current, but it is not following the linear relationship between V and I. When we are having this positive value of voltage, so this is our origin 0, 0, 0. So for these positive value of voltage, this current first increases suddenly and then it starts increasing and there is a flow of current. And the current is in milliampere, like I have shown it here as 1.5 milliampere. So for the positive values, it has in the range of milliampere. But if you come to the negative values of the voltage, if you come to the left side of the origin, then this shows the negative value of the voltage. So for the negative value of the voltage, the current is almost very low value. It is almost zero up to this region. Then abruptly it increases and then there is a breakdown region. So this VI characteristic graph is for a diode, because diode are unijunction devices where the current flows only in a single direction. So for the positive value of the voltages, there is a flow of current. The current is in milliampere, but whereas for the backward direction, there is almost no or zero current. It is in microampere. It is very less in comparison to the positive value, and then it reaches to the breakdown region. So whenever you talk about a diode also we will study in our unit of semiconductors. So whenever there is a junction of semiconductors, then there is not an ohmic relationship between V and I. So this is a typical diode characteristic graph. This is a VI characteristic of a diode. So here it is not following the Ohm's law. It is not following the linear relationship between V and I. So second violation of Ohm's law is that when V and I depends on the sign of V, it has a different value of current for the positive values of V and different values for the negative values of V. So for example, you can take a diode. So diode does not follow the Ohm's law. Now come to the third point, that for the same value of I, V is having more than one value. Say here you can see, here also I have taken a semiconductor graph for a semiconductor and it is not following the Ohm's law. Say we can take any semiconductor, for example gallium arsenide. This is the symbol, G is for gallium, AS is for arsenide. This you can easily write down. You're familiar with the chemistry. So this is gallium arsenide. So here you can see that we have plotted a VI characteristic graph. That means the graph between the voltage and the current for this material, and here the voltage is in volts and the current is in milliampere. So if you go through the graph, then initially you can say that it is almost linear, but suddenly it shifts to the region where it is non-linear. The relation between V and I is non-linear. Here you can see it is not following a linear relationship. So this region we call as a non-linear region between V and I. And then what happens if you come to this negative resistance region? That means that the value of I is decreasing with increasing the value of voltage. Our Ohm's law is V is equal to IR. So that means if we are increasing the V, then corresponding I should also increase. But as you see in this region, that as we are going increasing V, because in this direction the value of P is increasing in volts. So as we go on increasing the value of voltage, the value of current is continuously decreasing. So on increasing the V, I is decreasing, that means R should have negative value. So this region is named as negative resistance region. This simply means that increasing the voltage is decreasing the current. So this graph has different regions. This is the linear region, this is the non-linear region, this is the negative resistance region. So here you can find out that for the single value of I, say if I take this value of I, it may have any value. So if I find out the corresponding value of the voltage, then if I go like this, then this is the one value of voltage and it cuts the graph here also. So these are the two values of the voltages I am getting for the same value of current. So V is equal to IR. It is not possible to have two values of I or more than two values of V for a single value of I. So this is again a violation or a limitation of the Ohm's law. So we can say that all the metallic conductors where current flows easily, they follow the Ohm's law. But whenever you go to the diodic structure or semiconductor structure, then there is a limitation of the Ohm's law. And all the 3 points we considered, you have to keep in mind, then the Ohm's law is not followed.
Next topic we are going to study is resistivity and resistance. Let's begin. Resistivity of materials. So all the materials we categorize into three basic categories. They can be either metals or which are very good conducting, or semiconductors which are conducting but not as good as metals, and the third category is insulators which are not at all conducting. So the resistivity, since the metals are very good conductors, so the value of conductivity is very high, and if the conductivity is high, that means the resistivity is very low, since conductivity and resistivity are opposite to each other. So for the resistivity of metals, it has a very low value. It lies between 10 to the power minus 8, and the unit, we know how to write down the unit, ohm into meter. So it is ranged between 10 to the power minus 8 meter to 10 to the power minus 6 ohm into meter. So that is the very low value of the resistivity of metals. If you come to the semiconductors, then their resistivity is also low but not as low as metals. It is 10 to the power minus 5 ohm into meter, and it may be as high as 10 to the power 4 ohm into meter. Now last category is insulators, which are not at all conducting, so they have a very high value of resistivity, 10 to the power 5 ohm into meter to 10 to the power 16 ohm into meter. Now how to remember? If you see metals, then they have a very low value. That means it will always be in power negative. So 10 to the power minus 8 to 10 to the power minus 6. Now it ends at minus 6. So for the semiconductors, it will be having the value just below the 6. That means 5 but with a negative sign. So 10 to the power minus 5 ohm into meter, and it goes high up to 10 to the power 4 ohm into meter. So we stopped at 6, then we begin from 5, we reached up to 4. Now again, if it is insulators, then insulators will be having positive value because insulators have a very high resistivity. So again, minus 6, we will come with 5, but now with positive sign. So 10 to the power 5 to 10 to the power 16 ohm into meter. So these are the value of resistivities, which we represent with the symbol rho. Now if you remember the resistivity of all these three categories of materials, you can simply write down the conductivity, because you know the relation that sigma is just the opposite of resistivity. Sigma is equal to 1 upon rho. So if you just take the inverse of these quantity, then you will have the conductivity. So once the resistivity value is remembered, you can also remember the value of conductivity. So that is how we categorize the resistivity of material. Now how this resistivity rho depends on temperature. That is our next step, that how resistivity depends on temperature, because we said that resistivity depends on material only. It does not depend on the length or the cross-sectional area, it depends on which material we are taking. So it has a slight dependence on temperature also. So how it depends on temperature? That is we call as temperature dependence of resistivity. So the formula we use for the temperature dependence of resistivity is, we want to take resistivity at any temperature T. So this is rho with suffix T. This is resistivity rho at any temperature T. This is equal to rho at the reference temperature. What is the reference temperature we are taking? And with reference to this temperature, we are taking this, the first one, temperature T. So rho at any temperature T is equal to rho naught 1 plus alpha T minus T naught. T is the temperature we are considering, this is T, suffix T, and T naught is the reference temperature, and alpha is temperature coefficient of resistivity. So rho T is the resistivity at any temperature T, rho naught is resistivity at the reference temperature, and alpha is temperature coefficient of resistivity. So using this formula, you can calculate the resistivity at any temperature if the resistivity at some reference temperature is given to you. And alpha is the coefficient of temperature or coefficient of resistivity, temperature coefficient of resistivity. And it depends on resistivity as the inverse of temperature. Now we'll study that how this resistivity of the material depends on the type of material we are taking. So for example, if you take the material is form of nichrome, it may be nichrome, that is nichrome is a combination of nickel, ferrous and chromium. So that is known as a nichrome. Ni is nickel, Cr is chromium, and this is ferrous. So nichrome, it shows very weak dependence of resistivity on temperature. So if you take any of the nichrome wire, then the resistivity of this nichrome depends very little on the temperature. So rho shows changes very little with the temperature. So rho changes very little with temperature. That is why we use nichrome wires. This is the reason behind using the nichrome wires for the connections, because nichrome is the material which shows that the resistivity changes very little with varying temperatures. If we vary the temperature, then there is not much change in the resistivity. Now if you come to the semiconductors, so if you take any of the semiconductors, so what happens for semiconductors? The resistivity of semiconductors decreases with increase in temperature. Rho decreases with increasing temperature. So for the semiconductors, if we increase the temperature, then the resistivity decreases. What is the reason behind this? What is the reason behind this? Then we can show the resistivity formula as it is 1 upon sigma, 1 upon conductivity. And if we write down the formula of conductivity, then it comes out to be an E squared tau upon m. We calculated it when we were calculating the drift velocity and mobility and all these things we were calculating. Then we calculated the sigma is equal to n squared tau upon m. N is the number of electrons, E is the charge on electron, tau is the relaxation time, that is the time between two successive collisions, and m is the mass of the electrons. So n is the number of free electrons per unit volume and tau is the relaxation time. So what happens for semiconductors? That if we increase the temperature, then by increasing the temperature, the successive collisions between two electrons also increases. So just remember that for all the semiconductors, the resistivity decreases with increasing temperature or the conductivity increases with increasing temperature. So all the semiconductors, if you increase the temperature, then they conduct very good. If they are conducting good means increasing the temperature will increase the conductivity and decrease the resistivity. So for all the semiconductors, rho or the resistivity decreases with increasing temperature. Now we come to the metals. So the matters, they do not depend much on temperature. They depends on temperature but not up to much extent. What happens if you see the same formula for the resistivity, that rho is equal to m upon Ne square tau, then with the increasing temperature, the number of collisions do not increases much. So tau decreases with temperature. What happens? Tau decreases with temperature, and if tau decreases, then the resistivity increases. So for all the matters, rho increases with increasing temperature. It is just opposite to the behavior of semiconductors. So all the semiconductors, they are not very good at room temperature, but metals are very good conductor at room temperature. But if we increase the temperature, the conductivity decreases or the resistivity increases for metals. This is because in semiconductor, the number of free electron increases with increasing temperature. But in metals, there are already a quite very large number of free electrons. So these are not affected with the temperature. So these three things are put in star. You have to always remember nichrome we can always use, we always prefer, because the resistivity does not depend on temperature up to much extent. Semiconductors, on increasing the temperature, resistivity decreases, conductivity increases. Metals, on increasing the temperature, resistivity increases and conductivity decreases. So that is all about the temperature dependence of resistivity, and what is the reason we prefer nichrome, and what is the reason the semiconductors are not good conductors at room temperature. On increasing the temperature, the conductivity increases, or for metals, that what happens for the metals if we increases the temperature. So that is the 3 points that shows the dependence of all the resistivity on temperature. So if you want to take a snapshot of this page, you may have it because it shows all the 3 points. Also, you may note down, if you are interested, you may note down these values. For these values, you can easily calculate the resistivity as well as the conductivity. If you come to these 3 of the graphs, then we can easily find out that which one is representing what. Let us come quickly to the first diagram. So this is our first diagram, and where we have plotted the resistivity, which is in micro into centimeter, 10 to the power minus 6 ohm into centimeter, and on the x-axis we are having the temperature T in Kelvin. So if you put a thought into the graph, then you can say that there is a slight variation in the resistivity rho with respect to the temperature. It is varying very slowly with increase in temperature. So this should be obviously our nichrome, because the value of rho changes very little with the temperature. So we can say that this is the resistivity of nichrome as a function of the temperature. Here we have taken the absolute temperature in Kelvin. So this is for nichrome. There is a slight variation in rho. If you come to the second graph, then for here you can see that as the temperature is increasing, the resistivity is decreasing. You can see this curve in form of a hyperbola. So there is a decreasing resistivity with the increasing temperature. And the resistivity always decreases with temperature whenever it is corresponding to the resistivity of a typical semiconductor. So this graph obviously shows any of the semiconductor, because for the semiconductors, the number of collisions increases and the resistivity decreases with increasing temperature. Now come to the third graph. As you can see that it is having the same characteristic but just the opposite of it. That as we are increasing the temperature in this direction, it shows the increase in temperature, then there is a corresponding increase in the resistivity also. Rho is increasing with the temperature according to our relation. Rho is equal to rho naught 1 plus alpha T minus T naught. So here you can see that the increasing temperature causes an increasing in the resistivity, and the resistivity is also of the order of a matter. So for all the matters, the resistivity increases with the increasing temperature. So this graph corresponds to a metal. What happens if in metals you are already having that number of free electrons there? So whenever you increase the temperature, it does not shows any increase in the corresponding collisions. And also it is practically observed that the resistivity increases with increasing in temperature. So if it is almost constant, it is a nichrome. If it is decreasing, it shows a characteristic of a semiconductors. It may be also characteristic of the insulators, because for insulators also what happens that it decreases with the temperature. But insulators we are not considering here because we are talking about the current electricity, and insulators are not in the picture now. And third is the metals, and for all the metals the resistivity increases with increasing temperature. The next thing we come to is the resistance. Resistance is always what that is resisting the flow of current or the flow of charge carriers. The thing which is try to stop the flow is termed as resistance. And the symbol we use from our earlier classes is this is the symbol we use to show the resistance. So if there is a current which is flowing and this is the thing which is to stop the current, then we call it as a resistance R. And you might have seen all this resistance in the form of rheostats you might have seen in your laboratories. And if you don't know, then what is there, you have this rod-like structure, and over that closely bonded wires are there. So this is why I'm showing some closely bonded. These are much closely bonded than what I am showing here. So here we have a bundle of wires which is closely wrapped over this type of structure, and this produces resistance within the circuit that is present. So this is here to produce the resistance, and you know that the resistance, the formula for resistance is equal to R is equal to rho L over A. So this is the resistivity which has a fixed value for any of the material. It slightly depends on temperature, but we consider it as a function of material only. It does not depend on the length or the cross section, but the resistance R depend on the length and the cross section. So if we increase keeping the cross section as constant and rho by taking the same material, if we increase the length L, then the resistance will increase. So if you want a long distance, so if you want a high value of resistance to be present in the circuit, we have to take a long wire. Because if you take a same wire, then the rho is fixed, material is fixed. For example, if we take the wire of say constantan or nichrome or manganese, because they have low dependency temperature resistivity, so we take the wires as nichrome wire because they have low resistivity dependence on temperature as we just studied, or you may take it to be constantan or manganese. So rho is fixed now, and if you take the same wire of the same cross-section area, then rho and A are fixed. But again, if you want to take the high resistance, then you have to take a long lamp. That means you have to take a bundle of wire if you want to increase the resistance, if you want to produce a high value of resistance into any circuit. So these type of resistance we call as wire bound resistors. Because we are using a long length of wire, so these are known as wire bound resistors. So is there any alternate if you want to not to use such long bundle of wires, and how to put them? They are quite bulky. So is there not any option present if we can replace all these wire bound resistors with the small ones? And that is quite easy to use, and we can easily put some resistors with the desired value into some of the circuits. Yes, there is an option. So instead of these wire bound resistors, what we use is known as carbon resistors. These are called as carbon resistors. These are very small, very handy, and very easy to use. You need not use long bundles of wires. And these are termed as carbon resistors. Then this type of resistors we can use up to a very high range, and these are known as carbon resistors because they are mostly made up of carbon. So what is the advantage of using these carbon resistors? First of all, they are very much compact, they are very much small in size. That means they are easy to handle, they are easy to carry, they are easy to use into any of the circuit, they are handy. And second is, they are inexpensive. Economically, they are quite affordable, so it has all the utility of a compact size and inexpensive. So that is why they are extensively used in all the electronic circuits. and these are very small, so you cannot read out the values, and for that we use a very important thing that is known as a color coding. So for all the carbon resistors we use color coding. We use a color to represent a code for the corresponding resistance. That means we are having the resistance but we cannot mention the value on these small sizes, so we just use a color to represent. So all these colorful resistors are bringing color to our electronic circuits, isn't it? Yes. So first of all, let's see that how they look. So here I am trying to draw a carbon resistor. So these are the cylindrical form. These are very small, but just to represent, I'm just making a picture of these carbon resistors as such. Here are the carbon resistors, and here we use different colors. So say we will go into the colors, but let us first see how colorful they are. So you may use a red, red again, and one more red. And this maybe and this I'm just using to represent the silver one. So this is the silver one. So you can show it to be that this is obviously red. Then we are having one more red. And there is a third red. And this may be a silver one. So I'm just representing silver with this color. One more resistor I can draw here. Say this is one more resistor I have drawn, and it is also having some color coding. Say for example, now you can take different colors. It may be a yellow, right? So we may write this. It is a yellow. Then we may have a violet, and it may be brown, and then a golden. So such type of carbon resistors are present. Now how to read this coding? It is a very interesting thing, and let's move to how to read this coding. So let us see how do we coding for such carbon resistors. So here I have drawn a table, as you can see, which has 4 columns into it. First shows the color. There are different colors: black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, silver, and in the end no color. So it has a different range of color, and there is some number. Black has 0, brown 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7, gray 8, white 9, and the third column has a multiplier. Multiplier means whatever is the number. See, black is having 0 and brown is having 1. So whatever is the number, you have to add it to the 10 to the power. If it is 0, then 10 to the power 0. 10 to the power 0 is 1. Brown, it is having 1. So 10 to the power 1. Red, 2. 10 to the power 2. Orange, 3. 10 to the power 3. Yellow, 4. 10 to the power 4. So whatever is the number, we will make it 10 to the power 10 to the power 5, 10 to the power 6, 10 to the power 7, 10 to the power 8, and 10 to the power 9. So if you remember the number, you can simply do the multiplier by putting it in 10 to the power. And tolerance is only given for the gold, silver, and no color. Gold is having 5% tolerance, plus minus 5% tolerance. silver is having plus minus 10% tolerance, and no color is having plus minus 20% tolerance, because this tolerance is in percentage. So if you are having a color coding, then how to do? As we have just seen that there are 4 bands. So 4 bands, how to write down these bands? They have written 1, 2, 3, 4. These are the 4 bands. So first band will represent a figure. Whatever is the figure, it is 1, 2, 3, 4, 5, 6 or 0. Whatever is the figure. Second also shows the figure. It is 1, 2, 3, 4, 5, 6, 7, 8, 9 or 0. Whatever is the figure. So first 2 band will give us the figure. Third band will give the multiplier. So whatever is the number, put it into 10 to the power the number you have. The fourth one is the tolerance. That is only for the gold, silver and no color. Gold 5, silver 10 and no color 20. Then we can do it very simply. Now let us say that the first one we are having is red. So red corresponds to 2. So we will put the figure as 2. Second one is again red. So red corresponds to 2. So the second figure will be again 2. Third band is again red. So red will have the multiplier 10 to the power 2. So this is 2, 2, 10 to the power 2. Then tolerance. Tolerance you need not write down. For any of the other color, you have only silver, gold. You have only gold, silver or no color. So say if the fourth band is silver. So then silver corresponds to plus minus 10%. So if you have red and silver, then you have 22 into 10 to the power 2 and the tolerance is plus minus 10%. Let us quickly see the carbon resistors and then write down the value. So this is red says 2. Again is red says 2. Third is the multiplier, that means 10 to the power 2. And this is silver means plus minus 10%. So the tolerance is plus minus 10%. So we have easily read this carbon resistor. Now come to the second carbon resistor. First is yellow. Yellow means the figure. Yellow shows 4. So this is 4. Second is violet. Violet will give us the figure. Violet says 7. So this is 7. Third shows a multiplier. So multiplier means 10 to the power brown. Brown give us as 1. 10 to the power 1. 10 to the power 1. And golden shows the tolerance of plus minus 5%. So this resistance is 47 into 10 to the power 1. And the tolerance is plus minus 5%. So if you remember this column, you can easily find out the resistor. Now the thing is how to remember the column. So we have to use a trick to remember the column. What is the trick? Just you have to remember this color with the figure. Because once you know the figure, you can do the multiplier, put it 10 to the power, right? So let us, whenever we want to make a trick, we use only the initial ones. So this is B, R, O, Y. So this is B, Roy. Okay, it is done. B, R, O, Y is B, Roy. Then G, B, V, G, W, G, S, N. So how can we make it? It is just a trick to remember. Just always remember a simple trick to remember. So you can remember it as B, Roy. That is the name of a person. B, Roy. You can say B, Roy. Black, brown, Roy. Okay. So this B, Roy, GB. B, Roy of Great Britain. Grey is green and B is blue. G is green and B is blue. So B, Roy of Great Britain. VGW. Very good wife. V is violet. G is grey because green we have already taken. So G is grey and W is white. So B, Roy of Great Britain, very good wife. Now you have to remember the tolerance also. So with 5 gold, 10 silver and 20 no colors. So BB Roy is any person who lives in Great Britain. He has a very good wife, and this wife has 5 golds, 10 silvers, and 20 no colors. So BB Roy of Great Britain, very good wife, 5 gold, 10 silver, 20 no colors. So you can easily remember, start from 0. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you go up to 9, then start is like black, brown, red, orange, yellow, green, blue, violet, grey, white. Okay, so BB Roy of Great Britain has a very good wife with 5 gold, 10 silvers, and 20 no colors. So if you want to put this, you can simply put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you want to put the multiplier, then 10 to the power 0, 10 to the power 1, 10 to the power 2 corresponding. And you need not remember the tolerance because she already has 5 gold, 10 silvers, and 20 no colors. So using this code, you can write down any of the color coding for the carbon resistors. The only formula is so simply we have to remember a person BB Roy, Mr. BB Roy. He is of Great Britain. He has a very good wife, and this wife has 5 gold, 10 silvers, and 20 no colors. So again, if I ask the same question, we have no resistors. But again, if I ask the same questions that you have a red, 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 and then you have a silver, then quickly find out this carbon resistor is red. Red comes to third one, so this 0, 1, 2, so this shows 2, this shows 2, this is a multiplier 10 to the power 2, and silver, how many silvers she has? 10 silvers, so that means this is 22 into 10 to the power 2 and plus minus 10%. So see how quickly you can solve now. Here the tolerance means that this must be a variation in the resistance. It may be plus minus 10% because we do not have always accurate values. So the value may vary between plus minus 10%. So that is what we call as the tolerance. So now you know all the significant figures, you know the multiplier, and you know what is the tolerance, and you know the color coding for each color. So you can always read out those compact resistors and write on their value very easily. So our next topic is electrical energy and power. So to find out the electrical energy and power, we consider a current which is flowing between 2 points. So let us say we have 2 points A and B. So this is a point A, say, and this is our second point B, and between these 2 points the current is flowing, and these 2 points are at any of the conductor. The potential at point A is V is a function of A because it's a function of position V at B. So these shows the corresponding voltages at point A and point B. And when the current flows from A to B, that means obviously the point A is at higher potential with respect to B. Because the current is flowing from A to B, that means the electrons will be flowing in the inverse. That means the electrons will be flowing in the direction reverse to it. That means point A is always at higher potential with respect to point B. So if you want to find out the potential difference between these 2 points A and B, then we can write down the potential difference as potential difference at point A minus potential difference at point A minus potential at point B. And since this potential is always higher, so it will have a positive value. So this difference is always greater than 0. Now let us say that in time interval delta t, we have a charge delta q which travels from point A to point B. Because there is a current flowing, so we can say that there is a charge delta q which is flowing in time delta t from point A to point B. So we can easily write down the current. This is delta q upon delta t. That is the average current we can write out. So if there is current, then we can write down the change in potential energy. This will be equal to the charge into change in potential. This will easily give us the value of potential energy. minus of V, and if you put in the value of delta Q, then it is I into delta T. So this is the value of the change in potential energy. And where this potential energy goes to, it comes up to the kinetic energy. So we can write on the change in kinetic energy. Whatever is the gain in kinetic energy is the loss in the potential energy, because all the potential energy converts to kinetic energy, and vice versa. So we can get the value of the change in kinetic energy is equal to I delta T into V. This will have a positive value, that means it will be greater than 0, and here if you're having a negative value, that shows it is less than 0. So it is having a negative value, and the kinetic energy, change in kinetic energy, is having a positive value. So what do we conclude from this? We conclude that if the charges are moving freely, we are having some freely moving charges, which are the free charge carriers, and they're under some electric field, then their kinetic energy will increase. So what we conclude, if the charges are moving freely under electric field, the kinetic energy will increase. So here we have calculated the change in kinetic energy as well as the change in potential energy. So this change in potential energy is always due to the work done. So whatever is the change in potential energy, we calculated as minus I delta T into V, and that corresponds to the work done. So whatever is the work done will be always equal to this value I delta T into V. That is the work done. And if you want to calculate the power, then power P is equal to work done upon the change in time, because power is always the rate of work done. So this is the work done, and if we divide it with the change in time, then it corresponds to the rate of work done. So power gives us delta W upon delta T. So if you put the value of this delta W, it comes out to be I delta T V, and if you divide it with delta V, you will get it as I into V. So whatever is the power, it comes out to be I into V. This is very simple a formula, but this is very, very important for all of your numericals. You will have all many number of numericals based on this formula. P is equal to IV. Like Ohm's law, always keep in your tips, but whenever you are calculating the electric, like Ohm's law, always keep it in your tips that whenever you are calculating the electric power, it is I into V. And what is our Ohm's law? V is equal to IR. So we can also substitute this V as IR. So put the value of V, it is IR, that means it will be I square R. So P is equal to, either you can use I square R or you can use I into V. But it depends on the condition of the numerical, which formula you have to apply. If you have to use the current with the corresponding resistance, then always use the formula P is equal to I square R. But whenever the voltage is in picture, then always use the formula P is equal to IV. Because if you remember the one, the second will automatically come. But when to use which one depends on the numerical. So just put a thought into it, that if we are utilizing the voltage or the resistance into the picture, then use the corresponding formula. So this gives us the power, the formula of power. And one more thing we can use, here we have substitute the value of V. Similarly, we can substitute the value of I also. So I will be V upon R. So just put the value of I. So this will be V upon R into V. So this will be V square upon R. So this is just the three representation of the one thing, but three are equally useful. You have to use a combination of voltage with resistance, or combination of voltage with current, or only current or resistance. So just use that logic and use any of these three formula to calculate the electric power, right? So we have calculated the potential energy, and this potential energy has a negative value. So the corresponding kinetic energy will increase, and we say that the charges are moving freely under the electric field, their kinetic energy will increase. But what happens in the actual conditions if we are using actual conductor? This energy is dissipated as a heat. So whenever you are using a circuit, some amount of heat is produced, and this heat is produced due to the increase in kinetic energy. So we have derived with two important formulas, the change in the kinetic energy or the change in the potential energy, and the power, that is the electrical power. So if you want to calculate the power which is dissipated, for example, the power supply to our home, it is coming from the power station. So how it comes? It comes through the connecting wire. So these are the connecting wires that connect the power station to the devices at our home. So these connecting wires from power station to device of our home, let us say that these connecting wires are having the resistance RC. C is for the connecting wires. So if you want to calculate the power loss in these, so this will be I square R, because R is here. So we have to use either this or this. So if the current is given, then you will use I square RC, and so this is the power which is dissipated through it, the power which is lost in the form of heat. So this power dissipated is equal to I square RC. Now we know the relation of the power which is there and between the current. So P is simply P, the power that connecting wire is having is P is equal to I square R. So if we put the value of I square, so again we simply use the relation P is equal to IV, that gives us I is equal to P upon V. So you can put this relation over here, so that the power which is dissipated through the connecting wires is equal to P square, the power given, upon V squared in RC. So the power which is dissipated is directly proportional to the resistance and inversely proportional to the square of the voltage. So what we can say, that the power which is dissipated in the form of heat, or the power which is wasted, because that is wasted in the form of heat, it is of no use. So the power wasted is inversely proportional to the square of the voltage. So if you want to less down, if you want to make this value of power wasted as low, then we have to increase the value of this voltage. That is why high voltage transmission is done. That is why we are having a high voltage wires which are running from these power stations to our home. So why this high voltage transmission is done? So due to this high voltage transmission, the power which is wasted in the form of heat, or the power dissipated, which becomes less. So this is the reason for high voltage transmission to our household from the power station. Resistance is a very simple thing, and the symbol we use to represent the resistance is always R, and it is drawn as like this. So this shows a resistance which is present in any of the circuit. So now we use this number of resistors which may be combined in different ways along a circuit. So let us say that we are having two such resistors. Say this is our resistor 1, we have drawn it like this, and this is our resistor 2. And they are connected from one side, that means they are in series. Say this is our resistor R1 and this is our resistor R2. So these are connected only from one side, and let us flow some current through them. Say I is the current which is flowing through these two resistors, and here we can say that is a point of contact somewhere here. So there is a point of contact somewhere here. So the current continues flow like this, it goes to resistor R, and then it comes out as I. So whatever is this is shown as a form of combinators. So two resistors, we say in this way they are connected in series. If the one end is connected, then they are in series. If both the ends are connected, then they are known as in parallel. So the same amount of current is flowing through it. So how we are flowing this current? Because we are applying some potential difference, we are applying some voltage across it. That is why there is a flow of current. So there will be some potential drop. Always remember that whenever you are having any of the resistors, there is a potential drop. There is a voltage drop across it. That is the only function of the resistor, that it has always a potential drop across it. So the potential drop or the voltage drop across R1 is, say, V1. V1 is the voltage dropped at the resistor R1. So the current is I. So V is equal to IR. So V1 is equal to IR1. This is the potential drop across resistor R1. And similarly, the potential drop across the resistor R2 will be V2 is equal to current I, same, IR2. So these are the voltage drop across R1 and R2. Voltage drop or potential drop means the same thing. So here we are having the potential drop or the voltage drop V1, and for the resistor R2 we are having the voltage drop or the potential drop V2 is IR2. So we can calculate the total potential drop. So the total potential drop comes out to be the sum of these two. V is equal to V1 plus V2. So simply put the value V is equal to IR, and V1 we have already calculated. Current the same because these are in series. So V is equal to IR1 and V2 is equal to IR2. So I is common throughout the equation. So this I cancels out in these three terms. So we have R is equal to R1 plus R2. That means the total resistance of the system will be the sum of these two. So this is known as, we can call it as equivalent resistance, or the total resistance of this arrangement is equal to the sum of the two resistors which are connected in series. So whenever we are having a number of resistors which are connected in series, we have to simply add them and get the equivalent resistance. So if we have many resistors in place of these two resistors, say we have n number of resistors, so we can call them as, for many resistances in series, we can calculate the equivalent resistance. R equivalent is equal to R1 plus R2 plus R3 and so on, and this continues up to, say, n number of resistance we are having. So this continues up to Rn. So whatever is the number of resistance, simply add them up and get the equivalent resistor of that system. So that was the first type of combination we have done, and we are calling it a series combination. Now the second combination we will do when we'll connect the both the ends of the resistor, and that we could. Now we'll do the second type of combination where we will attach the two ends of the connector, and that we call as a parallel combination. So say we are having a resistance R1 and this is another resistance R2, and if we connect both the ends, so say both the ends are connected to a common point from here and from here, we are having a common point, and through these points we are allowing some current to flow. Say the current is I, and the current coming out will also be I. But here, after reaching to this point, it is divided into two parts. Say here the current is I1 and here the current will be I2, because whenever two are in combination as parallel, always you have to remember that for the parallel combination, voltage remains the same. That is a thumb rule for parallel combination, that always the voltage remains the same, because the potential drop across both the ends is the same, potential difference across both the ends is the same, so the potential drop is always same. So we can say that the voltage is same, so we can use the Ohm's law. For example, voltage across the first resistance, the current is I1 and the resistance is R1, so V is equal to I1 R1, and if we apply the Ohm's law to resistor R2, then again we have the potential as same, V is equal to I2 R2. Because in parallel combination, always the voltage is same or the potential is same. Series current is same and parallel voltage is same. So now we can calculate the total current, because the current is divided into two parts, I1 and I2. So if we calculate the total current I, then we can simply write as I will be equal to I1 plus I2 because the current entering is I, the current coming out is I. Here it is divided into two parts, I1 and I2, and here again if you come to this part you will have the current as I1 and here you will have the current as I2. So this I1 and I2 combines at this point and again you will have this total current as I. So I is the sum of I1 and I2. Now substitute the value of I1 from this equation and substitute the value of I2 from the second equation. So what you have, I is equal to V upon R, I1 is equal to V upon R1 and I2 is equal to V upon R2. So V is common throughout the equation. So this gives us the equivalent resistance or the net resistance across this will be 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2. So this gives us the formula for the equivalent resistance of the combination of two resistors which are connected in parallel. So this is only a system of two resistors. If you have a system of n resistors, then also you can generalize. The same equation. So if you have many resistance in parallel, so you can write down for many resistance in parallel. So you can write down 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on. And this continues up to the nth value of the resistor, that is 1 upon Rn. So this is the term we have generalized for the n number of resistors which are connected in parallel. Now we take a third type of combination, where we have a combination of series as well as parallel. So let us say that we are having this resistance R1 and this is in series with two more resistances which are in parallel. So R2 and R3 are in parallel combination and these two are connected in series with the resistance R1. So we have a combination of series and parallel. So the current we will be flowing here is I and then it will go up to here. Again it is divided into two parts. Say I1 and I2 because through R1 it is only I. So say I1 I here, I2 here. Then it comes out at I1 and I2 and again it will combine and here we will have it as I. So we want to calculate the total resistance for this combination and this total resistance we call as R equivalent. So R equivalent is equal to this is the equivalent for all the three resistances. So we call it R equivalent of 1, 2 and 3. This will be equal to R1 plus this combination because in series we simply add. So this and this is in series. Say this is our second combination. So this combination plus R1 is in series. So R1 plus this equivalent of this. So we write it as equivalent of 2 and 3. Right? Now we want to calculate this R equivalent of 2 and 3. So these are in parallel. So simply apply the rule for the parallel in combination. So 1 upon R equivalent for 2 and 3 is equal to 1 upon R2 plus 1 upon R3. And this may be written as R2, R3 and in the numerator you will have R2 plus R3. So that gives us the value of R equivalent of 2 and 3 resistor combination is equal to R2, R3 upon R2 plus R3. Now simply add it in the final equation. So we will have R equivalent of all these 1, 2, 3 as R1 plus R2, R3 upon R2 plus R3. Right? So this is this R1 plus this equivalent. So that is the total equivalent resistance. So how would you do this? Simply solve this. Take it as in the denominator R2 plus R3. So here you will have R1, R2, because R1 is there and you have to multiply it with R2 and then R3. R1, R2 plus R1, R3 plus R2, R3. So that will give you the R equivalent of all the three resistors 1, 2 and 3. So that is how you can calculate the equivalent resistance of series and parallel in combination. And if you know the resistance, then simply you can calculate the current using the Ohm's law. V is equal to IR or I is equal to V upon R. R here is R equivalent of all the 1, 2, 3. So this will be simply multiply the above equation with V. So this is V R2 plus R3 because R equivalent is in denominator, so we have to inverse the equation upon R1 R2 plus R1 R3 plus R2 R3. So that will be the current. So this is how you can do the series combination, you can do the parallel combination, or you can do the combination of series and parallel in combination. Simply using these three formula. Always keep some tips and do your numericals because it works easily everywhere. Only you have to pay attention that these are in series, that means the current is same, and if these are in parallel, that means the voltage is same. Then calculate the equivalent resistance. How much complicated is the system? Just go on by calculating the equivalent resistance and that will give you the final voltage, final resistance and final current. So that's all for this lecture. If you like this lecture, then like and share and subscribe to our channel Physics Class so that you can continuously receive notifications for all the new lectures. Keep them watching. Thank you.